In section 7.2, we look at sums of terms of arithmetic and geometric sequences. Let's take a look at a special problem. Suppose we wish to sum the numbers from 1 to n. So we're talking about 1 plus 2 plus 3 plus 4 plus all the way up to some positive whole number n. It turns out that this sum is n times n plus 1 divided by 2. And I'm actually going to show you why this is the case. So let's just imagine if we were adding up the first 8 numbers. So suppose I had 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. And we want to know, what is this sum equal to? Now, of course, here I could just add up those numbers and it wouldn't be that hard to do. But to figure out a formula for this, let's realize that adding the numbers forward would be the same as adding the numbers backwards. So if I add up these numbers in reverse order, we get the same thing. So this is equal to the same sum. But something interesting happens now when I add these together. You'll notice that when we add the first two terms here, 1 plus 8, that is 9. And when we add the next two terms, 2 and 7, we also get 9. And you'll notice that every time, in fact, we are going to get 9. And so we are adding the number 9 plus 9 plus 9 plus 9 plus 9, etc. The only question is, how many times are we doing this? Well, our original sum went from 1 to 8, so there are 8 total terms, which means we must be adding up 9 to itself 8 times. Well, 9 plus 9 plus 9, etc., 8 times is simply 8 times 9. So this sum right here is 8 multiplied by 9. But you have to realize that what we did is we added these two sums together. So we have the sum plus the sum, so that's going to be 2 times whatever that sum is, right? So if I want to know what is that original sum, I need to divide both sides by 2. And so the sum of that original numbers, the original numbers that we had, is 8 multiplied by 9 divided by 2. So when you add up the first 8 numbers, you simply take the number 8, you multiply it by 1 more than 8, and you divide it by 2. And you can apply this pretty much to any number, right? So if I was adding from 1 all the way up to 80, then we would have 80 times 81 divided by 2. Okay, and it works for any number n. Now we can actually prove it for the number n. All we would have to do is replace the 8 with an n at the end. And then when you add all these numbers together, you would have n plus 1 every single time. And so you have n times n plus 1 divided by 2. So this is a pretty interesting summation formula. And this was actually figured out by a mathematician named Carl Gauss. And the story is that he figured this out when he was 5 years old. Okay, let's go on to arithmetic and geometric sums. So if we want to take the sum of the first n terms of an arithmetic sequence, the formula for doing that is given down here. So the sum of those first n terms is going to be a0 plus a1 plus a2 all the way up to an minus 1. And it turns out that the formula for doing this is n divided by 2 multiplied by 2 times the first term plus the common difference multiplied by n minus 1. And you can also express this by using this formula, which is n divided by 2 multiplied by the first term of the sequence plus the last term of the sequence. So you can use either of these forms for the sum. It just depends on the information you are given. So again, when you are trying to find the sum of the first n terms, you can either use this formula for doing that, or you can use this formula. Now, to use the second formula, you have to know what the last term is, what the first term is, and also how many terms you're adding up. To use this formula, you need to know what the first term is, what the common difference is, and also how many terms you are adding up. So let's take a look at an example. So in the first example here, we are asked to find the sum of the first 11 terms of the arithmetic sequence 2, 5, 8, 11, 14, etc. So we are looking for the sum of the first 11 terms. Notice that we do not know what the last term is, right? They don't show what the last term is, but we do know that we have 11 terms. We do know the first term is 2, and we can figure out the common difference by simply subtracting any two successive numbers. So for this particular problem, we know that n equals 11. We know the first term is 2, and the common difference is pick any two numbers and subtract them. Remember, you have to take the later number minus the earlier number. So 11 minus 8 is 3. So the sum of those 11 terms, according to the formula here, would be 11 divided by 2 multiplied by 2 times the first term, and the first term is 2, plus the common difference, which is 3, multiplied by n minus 1, which is 11 minus 1. Okay, so again, I'm just taking these values here, and I'm substituting them into this formula up above there. So now we just need to do the math on this. And when we do this, we get 11 divided by 2 multiplied by 4 plus 30, right? Check the math there. So this is 10 times 3 is 30. 4 times 30 is 34. And so we have 11 over 2 times 34. And of course, we know that 2 goes into 34 17 times, and so we have for the next one, we are finding the sum of all even numbers between 2 and 100 inclusive. To do this, we'll use the second formula. Second formula says the sum is equal to n divided by 2 multiplied by a naught plus a n minus 1. Again, remember a naught is the first term and a n minus 1 is the last term. So to do this, we need to know how many terms are we adding up. We can see the first number is 2, the last number is 100. The question is, how many numbers are we adding up? Well, we're only doing the even numbers, so that would be 2, 4, 6, 8, etc. And from 2 to 100, it's not too difficult to see that there are 50 numbers that we are adding up there. So this is 50 divided by 2 multiplied by 2 plus 100. So this is 25 multiplied by 102. And this is 2,550. So that is the sum 2 plus 4 plus 6 plus 8 plus all the way up to 100, but only the even numbers. Next, let's talk about summation notation. So here we want to expand the following sums given in summation notation. Do not evaluate. So we are not interested in adding up the numbers. We just want to interpret, what does this mean? So for the first one there, you see you have this Greek letter, what we call sigma, and it says I equals 2, and then there's a 5 up above, and it says 3 times I. So what this means is you are going to add up the numbers 3 times I, starting at I equals 2 and ending at I equals 5. So for this sum, we will be plugging in I equals 2, 3, 4, and 5. And then we will add those up. So the first term, when you let I equal 2, you plug that in. That's going to be 3 times 2. Plus the second term will be I equals 3. So that's 3 times 3. Next term will be I equals 4, which is 3 times 4. And finally, we end with I equals 5, which gives us 3 times 5. And if you add these up, you have 6 plus 9 plus 12 plus 15. And if you do the math on that, you get 42. But again, they only wanted us to expand, so we don't really care what the answer is. We just wanted to see this portion of it. Let's do the second problem. So for this one, we are starting at I equals 3, and we're stopping at I equals 6. And you'll notice that the formula is a constant, right? It's just 7. There is no I in this formula. So we are going to find out what is the sum starting at I equals 3, and then 4, and then 5, and finally with 6. But there's nothing to plug into. So when I equals 3, the number is 7. Plus when I equals 4, the number is 7. When I equals 5, the number is 7. And when I equals 6, the number is 7. So for this one, it's just 7 plus 7 plus 7 plus 7 because it's a constant, okay? So the way you deal with summations is you take this number down here, which is called the index. That's usually why we call it I. And then you just plug in that number, and then you plug in every successive integer after that, stopping at the number on top. Now for the next example, what we want to do is the opposite. They give us a sum, and we want to write it in summation notation. So to do this, you need to think about what you have here. So this particular sum is -2, and then -4, I can think of that as plus -4. And then -6 is plus -6, right? And we're going to keep on adding negative, even numbers all the way up until we get to -20. And since there's not too many numbers here, I'm going to write them all down so that we can see the entire sum here. And then we need to formulate this. So you need to think about, well, what is the number -2, and how can I relate it to the number -4, -6, etc.? Well, -2 is -2 times 1. -4 is -2 times 2. -6 is -2 times 3. And you kind of get the idea. And the last one, -20, is -2 times 10. So if I'm going to write this in summation notation, I'm going to start at I equals 1, right? That's this number here. And I'm going to increase by 1 each time, stopping when I equals 10. And the formula is we're taking -2 and multiplying it by that index, by I. So this would just be the sum I equals 1 to 10 of -2I. And one final note that I'll make here is you don't have to use the letter I. So a lot of times we like to use the number K. So if I were to use the number K, this is what it would look like. You will also see some books, including this one, that will use the number J. Okay, but all of these are the same. This variable down here is kind of a dummy variable. It doesn't really matter what you use. Just whatever you use down here, you have to be sure to use that same variable in your summation. Let's talk about the sums of a geometric sequence. So a geometric sequence comes from adding up numbers that look like this. So we have A0 times R to the J power. J equals 0 to n minus 1. And if you have a geometric sequence, when you add all those terms up, the sum turns out to be A0 times 1 minus R to the n divided by 1 minus R. And again, n is the number of terms that you're adding up. Okay, you have to be kind of careful because when you have it in summation notation, n is not the number you see on top when you're starting at 0. Okay, so for example, if you go from 0 to 10, n is actually 11, right? So you have to be a little bit careful with that. But let's go ahead and take a look at this first example where it says to find the sum of the first 5 terms of the sequence given by aj equals 1/2 times 3 to the j. So to find the sum of the first 5 terms here, the formula says that S5 will be equal to A0 times 1 minus r to the 5 divided by 1 minus r. So it'll be a naught 1 minus r to the 5th power divided by 1 minus r. So to figure this out, we just need to know what is a naught, what is the first term, and what is r. Well, the first term is the term that you get from your formula here when j equals 0. Right? So a naught is going to be 1/2 times 3 to the 0. This is 1/2 times 3 to the 0 is 1, and 1/2 times 1 is 1/2. So a naught is 1/2. And then to get r, you can basically see r here. So remember in your geometric series, or geometric sequence rather, formula, r is the number that you're raising to the j power right there, okay? And you can see that that number is 3. So you can kind of see that r is 3 there. If you don't see that, you could always find a1 by doing 1/2 times 3 to the 1, which would be 1/2 times 3, which is 3/2. And then you can find r by simply dividing a1 by a naught, right? Just divide any two successive terms. That would be 3/2 divided by 1/2, and if you do the math on that, you get 3. So once I know that a naught is 1/2 and r equals 3, I can find the sum of the first 5 terms by just substituting 1/2 in for a naught and substituting 3 in for r. So we get 1/2 times 1 minus 3 to the 5th power divided by 1 minus 3. This is 1/2 times 1 minus 3 to the 5th power is 243, and 1 minus 3 is -2. And if we just do the math here, we have 1/2 times -242 divided by -2. And this is 1/2 times 2 goes into 242 121 times. And again, the negatives here are going to cancel out. And so we get 121 over 2, right? 1/2 times 121 is 121 over 2. In the next problem, it says finding the sum if a formula cannot be directly applied. So let's see what they're talking about here. So notice in your summation, you have the sum of 3 times 2 to the j minus 1 power. So we have to first ask, what kind of series is this? Well, it's geometric because you have something being raised to a power here, but we need to know the first term and the common ratio. Now, the trick here is that we're not starting at j equals 0. We're starting at j equals 1. So if you plug in j equals 1 into this, you're going to get 3 times 2 to the 1 minus 1. And then the next term, when you plug in j equals 2, will be 3 times 2 to the 2 minus 1. And then j equals 3 will look like this. J equals 4. And j equals 5. So what we need is, how many terms are we adding up? Well, we're starting at 1 and we're stopping at 5. So clearly this is 5 terms. We need to know what is the first term. Now the first term we usually call A0 or A naught. I'm going to say maybe let's not use that notation here, right? Maybe instead we'll just call it the first term because it does not correspond to j equals 0. So our first term in this problem is this one, and that is just 3, right? Because we have 3 times 2 to the 0 power, so that's 3. And then the common ratio r is clearly 2, right? Because 2 is the number that's being raised to the power each time. Now, once I have that, I can say that the sum of the first 5 terms here is going to be a naught times 1 minus r to the n divided by 1 minus r. And then we just have to go ahead and plug everything in. So a naught really is just the first term, that's 3. Then we have 1 minus 2 to the 5th power divided by 1 minus 2. And if we do the math on this, we have 3 times 1 take away 32 divided by 1 take away 2. So this is 3 times negative 31 divided by negative 1, which is 3 times 31, which is 93. So the sum of the first 5 terms here is 93. So again, the key to a geometric sequence or an arithmetic sequence is the first term. How many terms are you adding up? What's the common difference or the common ratio? And sometimes you also need to know the last term, depending on the formula that you're using, like for arithmetic sums. All right, let's take a look at another problem. So this next problem involves finding the sum of an infinite geometric series. So a geometric sequence that starts and stops at a particular number, we can find the sum of that by using the formula on the previous page. But what if you are adding up an infinite geometric series? So you have the numbers that are in a geometric sequence, but you're adding them up and you never stop, right? There is no last number. Can you find a sum? Well, you can if the common ratio is a number in between 1 and negative 1. So when we say the absolute value of r is less than 1, we're saying that r has to be a value in between negative 1 and positive 1. If that is true, you can find the sum of an infinite geometric series by simply taking a naught divided by 1 minus r. So remember, a naught is just the first term, and r is the common ratio. So let's take a look at the examples we have down below here. So to find the sum here, first of all, let's determine what is a naught and what is r. So in this example, a naught is the first term, which is 2. That's pretty clear. R is the common ratio. So I can figure out r by dividing 4 by 2, 8 by 4, 16 by 8, right? So I can do any one of these to figure out r. They should all be the same. And you can see that these are all equal to 2. And notice that the number 2 is not a number in between 1 and negative 1. So the only time an infinite geometric series has a sum is when r is between 1 and negative 1. If this is not true, there is no sum. So this has no sum. And what that means is basically if you add up these numbers forever, think about it for a second, you're going to get infinity, right? Because the next number you would be adding here would be 32, and then 64, and then 128. And if you keep adding larger and larger numbers, you're not going to get a sum. It's going to add up to infinity. Now, in the second example here, it's a little bit more interesting. The first term of the series here is 1. You can see that here. And the common ratio is take any two successive terms and divide them, right? So I could take 1/2 divided by 1. I could take 1/4 divided by 1/2, or 1/8 divided by 1/4. And if you do the math on any of these, you will see that r is 1/2. And the important thing here is 1/2 is a number in between 1 and negative 1. So this one will have a sum. And the sum of an infinite geometric series is the first term divided by 1 minus the common ratio. So for this problem, the first term is 1, and we're dividing that by 1 minus 1/2. So this is 1 divided by 1/2, and 1 divided by 1/2 is 2. So the infinite sum here is 2. And I know this can seem a little bit strange to talk about adding up infinitely many numbers and actually getting a sum. But basically what it means is that when you keep on adding more and more of the numbers in this series, your sum is going to get closer and closer to the number 2, right? So every term you add, you get a little bit closer to 2. And I would just encourage you to take a calculator and just start adding these numbers up, right? So if you add these numbers up, you should notice that it's pretty close to 2. And then if you add the next term, which would be 1 over 32, it would be a little bit closer to 2. So if you have the time, check that out. Now let's take a look at an application. This is an application of an arithmetic sequence. It says an auditorium has 30 seats in the front row. Each subsequent row has 2 seats more than the row directly in front of it. So the front row has 30 seats. The next row is going to have 32 seats. The next row will have 34 seats, right? And there's 12 rows in this auditorium. So how many seats do we have altogether? Well, we have to take the sum of this arithmetic sequence. And so here we know that the first term, A naught, is 30. We know that the common difference here is 2, right? Because each time it increases by 2. And the number of terms we're adding up is 12 because there are 12 rows. So we have n is equal to 12. And we can find the sum of these first n terms by using the formula n divided by 2 multiplied by 2a naught plus n minus 1 times d, right? That's the formula from earlier. So if we apply that, what we have here is 12 divided by 2 multiplied by 2 times 30 plus 12 minus 1 times 2. So this is 6 times 60 plus 11 times 2 is 22. So this is 6 times 82. And 6 times 82 is 492. So this particular auditorium has 492 seats. And for our last problem, we'll look at an example involving geometric sequences. So it says, suppose $2,000 is deposited initially and at the end of each year. So you're going to start by putting $2,000, and then at the end of the year, you're going to put in another $2,000, and then at the end of the next year, another $2,000, and you're going to do this for 10 years. So the question is, what is the total amount of money in the account at the end of 10 years if it pays 5% interest compounded annually? Okay, so we have to remember our compound interest formula. Compound interest formula says the amount of money is going to be the amount of money that you put in times 1 plus the interest rate divided by the number of compoundings raised to the power number of compoundings times number of years. Okay, so this can seem a little bit complicated, but we know n equals 1 because we are compounding annually, right? Annually means that you are compounding 1 time per year. And so if n equals 1, this formula becomes p times 1 plus r to the t. And we also know that r is 5%. So this will be p times 1 plus 5% is 0.05. And so this becomes p times 1.05 to the t. All right, so the initial $2,000 that you put into the bank, this initial deposit, the amount of money you're going to have there is going to be $2,000, that's the amount of money you put in, multiplied by 1.05 to the 10th power. Now, it's the 10th power because that money sits in the bank for 10 years, so it gets 10 years of interest. The money that you deposit at the end of the first year, right here, that money is also $2,000, but it's only going to sit in the bank for 9 years, right? Because again, you deposited at the end of the first year, and we're doing this for 10 total years. So you keep on doing this. The next deposit is going to sit in the bank for 8 years, right? And you do this all the way down to your last payment. Now, your last payment goes in the bank at the end of the 10th year. So it is not going to accumulate any interest. It's just going to be 1.05 to the 0 power. So what I want you to see here is that you have a geometric sequence, right? A geometric series, if you will. And the first term, I would like to say, is this one. okay? Because this first number is 2,000. And then the next one would be 2,000 times 1.05 to the 1. The next one would be 2,000 times 1.05 to the 2, etc. So if we think of this as the first term, this as the A0, then the common ratio R would be 1.05, because that's the number that's being raised to the power each time. And the number N is going to be 11, right? Because there are 11 deposits. You make the first deposit right when you start, and then you make another deposit at the end of the year for 10 years. So that's 11 total deposits. So we can find the sum of these 11 terms by using the formula for the geometric series, which is A naught times 1 minus R to the N, and N, of course, is 11, divided by 1 minus R. And then we just fill in what we know. We know that A naught is 2,000. That's the initial payment here, times 1 minus 1.05 to the 11th power, divided by 1 minus 1.05. And this I'll plug into a calculator. And the total that we get for this is this number right here. So that is $28,413.57. This is how much we'll have at the end of the 10th year.